Okay, I think we will start now. So hello and welcome. My name's Andrew Harris, and I'm a technology lead for an NFVI project at Telstra. With me today, Greg, Juniper product manager, and Anita, a Red Hat product manager for NFVI. So we're here today to talk about some of the experiences that we've had actually trying to implement an NFVI solution in Telstra, delivering a virtual router solution. So some of what we're going to be talking about today are some of the key business requirements that we are looking to achieve, what we're trying to make happen with this NFVI solution on OpenStack, and a couple of the key requirements that we have to deliver upon to make it real. So we need to ensure that we deliver on reliability, redundancy, while also delivering a scaled solution so that we can meet quite a strict unit cost that is equivalent or ideally much, much better than what we do on our physical infrastructure. So we talked through some of these problems, some of these design decisions that we've made, the workarounds that we've made in the short term, as well as some of the options that we need to work on in the future to try and make this more efficient and even more highly available and reliable and scalable. So our solution and our journey started about 2 years ago, and we kicked off a OpenStack deployment to try and virtualize one of our network components. And we were able, towards the end of last year, to successfully deliver upon that in just a limited field trial. We took that learning and we transitioned it to a new use case. That use case is a virtual PE. So this is an MPLS PE delivering IPVPN services. These for business and large enterprise customers. And we were using the latest version of OpenStack that was available at the time. So this is on Red Hat, so our OpenStack Network Platform 10. And we had strict requirements if we're going to transition from our physical to virtual on reliability, high availability, scale, and make sure that we robustly test it. And we give all of our business stakeholders confidence that the solution was going to not impact any of the existing services, and essentially be fully transparent for our customers. So the customers wouldn't even know they're on virtual in this case, but we get to offer a more efficient solution. So the business problem, basically we're looking to reduce costs. So today our design standard looks for quite large physical routers delivering all kinds of services. So our physical routers, they deliver at large bandwidth scale with QoS, with BGP, OSPF, all these services that our customers want to deliver their applications over the top. From our design point of view, we have a one-size-fits-all. And this, in some cases, is not the most economical or feasible way we should do things. So what we've been looking for as our business problem is to significantly reduce cost. That's our main key deliverable. Also, when we turn to OpenStack, we're also trying to reduce power and be much more efficient. So using the right size of solution for what our use case is. And the idea is that we reduce our unit cost per service and still offer the same level of service availability with features that our customers want. So really, this is what our business problem was and what we set out to achieve. So now I hand it over to Greg to talk a bit more about the background and context of delivering a virtual PE.
Yeah, good. Thanks, Andrew. Yeah, we got to save 10 minutes at the end for questions, but I wanted to maybe a lot of cloud people here give you some network perspective and what kind of network application we're delivering and why telecom network applications, NFVs, are so challenging and maybe go beyond what you'd normally see in an OpenStack cloud environment. The first thing that requires reliability and redundancy, and in this case, 50 milliseconds failover time. So you lose a virtual machine, you lose a compute node, you lose a whole location, 50 milliseconds, the network recovers. And the second one is scale. And the scale of layer 2 VLANs, which we'll get into a little more shortly. So a single virtual machine in this case can have thousands of VLANs or thousands of network flows, if you will. So those are two kind of bread and butter. Router has to do those things today. On a physical router, we want to do those things in the cloud as well. And sometimes people question 50 milliseconds. That's really, really fast. Why is that necessary? And the short answer is that networks were designed that way. It goes back to the days of optical failover, some optical technology called APS that could fail from one optical link to another in 50 milliseconds. So because networks are designed with the assumption that any wire or fiber that fails will switch over to another one in 50 milliseconds, we have to keep that design in place. And the implications of this are that if, for the sake of argument, we had a second of failover time, the network would detect within 50 milliseconds that something was wrong. And when it does, it'll update thousands of routes. Say there's a new route, there's a new path, this guy's dead. And that's sometimes called a route flap or a route update. And as those routes percolate through the network, that takes a little bit of time. You might see some black holes in various points in the network. And then when the 1 second happens, the compute node notices that something failed and switches over, you might flap back. So if you miss the 50 millisecond window, and maybe there's a little bit of flexibility to 100 milliseconds, you might see 2 route flaps. And I know that's challenging, but it's, since it's the way the networks are designed, today we're going to have to get as close to that as we can in the future. So we'll talk more about what we can do to get down to 50 milliseconds on any failure. Those are 2 key challenges, scale and failover. And so what is the application? This is sometimes called an MPLS provider edge. It's really a business VPN. A VPN in this case is isolating traffic between one, we'll say, in this picture I have a blue VPN and a red VPN, call it Foster's and Cascade for you Australian people, Australian beer drinkers. You have 2 different companies using the same infrastructure. This is not like an IPsec VPN, it's just a isolation at the network layer. They both pass through from the customer edge on the left, sometimes called a CE, through a layer 2 switching network to a PE, and that's the application that we're virtualizing in this case. They both use the same infrastructure, but they're completely isolated. No packet can go from Cascade in red to Foster's in blue. And the PE at the provider edge knows it's a Cascade network customer edge coming from the blue network by the VLAN. So we need to see the VLAN ID. We need to see the layer 2 information at the PE, or in this case, virtual PE. And then it maintains that red-blue coloring northbound to the P router. Think of that as the core router, if you will, and creates a separate VPN. And you can connect, single one of these PEs could connect dozens of breweries, for example, and thousands of different customers. So one PE is aggregating a lot of VPNs and a lot of networks. And here we're just showing 2, but there's more. There's many more than that potentially on one router. So that's just your MPLS VPN in a nutshell elevator pitch, but yeah, I'll open to questions later. So when we look at the other thing I should mention about this application, it's extremely valuable. This is super robust business network that can fail over in 50 milliseconds, so that businesses are going to pay extra for this. And it's got to be redundant in the sense that there's no single point of failure anywhere in the network. And if you look in the top left corner, that's the functioning network. There's 2 paths from the P to the PE to the CE. And so the failure cases that we look at within that are, for example, on that number 3 in the lower right, if something fails in the aggregation network, in the layer 2 piece of the network between the PE and the branch office of the CE, there's a second path through the aggregation network, so you can recover from that. Another potential point of failure is you lose a whole location. This would be perhaps we'll call it a central office or a POP, and that's number 2. If a PE fails, the P router will notice that whole location's down and find another path. And the third one, or labeled number 1 in the upper right corner here, which is the one we're going to dig into, is a fiber break or a network break between the PE and the P router. And these can be 10-kilometer fiber. This could be a fiber that runs under Sydney Harbor and pops up on the other side, or runs along George's Street in downtown Sydney. And so that's a pretty, it's a long, thin piece of glass. So it's possible that this could break. It's not an uncommon failure to happen. And if that fiber between the PE and the P routers that you see in number 1 were to fail, right, we need to recover immediately. Phone calls cannot be dropped, minimum packet loss, and the customer edge can't notice it. So that's the challenge that we laid out. And the question is, can we take that PE router, put it in the cloud, and still maintain this high level of availability? And that's what Andrew's built.
Thanks, Greg. So what are we looking for, or what are we looking at in terms of the options from OpenStack? So we have a couple of different options. The bulk standard one that comes with most OpenStack deployments is OpenVSwitch. So with the Neutron and ML2 plugin, you get OpenVSwitch, and you can run a virtual router on your controller nodes, and it's a fairly standard deployment, and we're going to talk about that one in particular a bit later. Other options that we have include SRIOV, so single root input-output virtualization, and essentially what we're talking about here is we get hardware acceleration. We get to bypass the kernel for packet processing, and we can get far accelerated rates than what our normal OpenVSwitch-based deployments can do. And then we have a kind of a hybrid model where we're trying to accelerate our OpenVSwitch with DPDK technology within the kernel itself and get some packet processing in the hardware. So as we move on to where our next deployments go on. So on the next slide, we end up with what it looks like with an OpenVSwitch deployment. So OpenVSwitch, when we add it into our virtual PE use case and a networking fabric, which we typically have for connecting computes together, our pathways that Greg spoke about suddenly look like this. So the diagram on the left shows there where we now have a packet flow going through a network fabric into a OpenVSwitch or virtual switch into the provider edge, and before it gets passed off to our customer network through the same path. This introduces a lot of extra failure points. And the key challenge that we have when we're doing these extra hops is detecting failures. So how do we detect failures quick enough across all these multiple hops to ensure that we comply with our requirement of 50 millisecond failover? This is a really big challenge. So we want to be able to detect on every single link here very, very quickly to both endpoints that a physical link as well as a logical link is down. And then those endpoints can react to that failure and go via a different path. So with the OVS solution, what we found through quite a lot of lab testing is that we weren't able to achieve our requirement, not by a long way. So we had to look for some alternate technologies to deliver upon our strict requirement. So one of the other options that we typically turn to in networking is an overlay. So we have an overlay protocols, and one of the key ones that we like to use is BFD, or bidirectional forwarding detection. Essentially, this is a very fast hello that goes between the two endpoints that you want to control. So in this case, we would have a fast hello between our virtual provider edge and two other endpoints, our core infrastructure, and they represent two links. They're trying to represent two physical links. And the idea is that if we lose, due to link failures or a process failure, any of those packets, so this is configurable, typically 3, we consider that link to be dead and we transition to another link. What we found, though, through our testing is that the BFD sessions were being hashed over a single physical link. What this means is that a single failure now can cause, from the PE's perspective or the core's perspective, a full outage. And this causes transitions over to a redundant site, but that can cause packet losses as well. And so we want to avoid that kind of failover when we don't need it, so for maintenance purposes or for any kind of patching that we want to do in our network. And so clearly, this solution, through our testing, was not able to meet our requirements either. So what we were looking at as trying to resolve the technical problem is the use of SRIOV. And in this case, what we've done is that we've actually tied one-to-one our physical network port to a virtual network port on our virtual PE. And this had the nice benefit of being able to instantly communicate link failures to both endpoints, and we were able to transition very, very quickly. So while it's not ideal and not really using all of our cloud flexibility, it did allow us to transition from in this case, for this particular requirement, from a physical to a virtual, while still complying with very, very fast failover detection and reaction. So now I'll pass it on to Anita to talk a bit more about future options.
Right. So thanks, Andrew. So we're going to go back to the OpenVSwitch option that Telstra was looking at initially and see what we can do to fix this solution or help with this solution on the OpenStack side. And if you look at this deployment, we're seeing traffic, it's bidirectional traffic, going from the access side, which is the CEs, or the customer edge on the left, and then going through to the VPE, the virtual PE, which is the VNF, and coming back down on the core side through the P router. And during this course, it has VLAN stacks on the left-hand side on the CE egg, and then the PE processes it and puts MPLS tags on the way out. And the traffic goes through on the compute node. You can see the typical deployment is an OpenVSwitch bridge, 2 levels. You have a BREX followed by a BRINT. And the traffic, the BREX is per individual NIC or NIC bonded link coming in, and then it's integrated or aggregated onto the BR integration bridge. In this case, if you look, there are other NICs as well, but these are NICs for not data path links. They are NICs for control plane, and there's NICs for OpenStack API, and there's for upgrade and install purposes. But let's look at the issue, which is on the core side of the network, where Telstra would like to detect link failure really quickly. And the link that we're looking at is between the BREX bridge and the top of rack switch. They have bonding turned on over here because there should be link redundancy. And you can use LACP or lag with LACP, Link Aggregation Control Protocol, to detect link failure quickly, but LACP isn't fast enough. The fastest interval is about a second. And we want sub-second failure detection here. So another option is to enable BFD on the lag, where they have BFD going out on each and every individual link. OpenVSwitch would have to turn on BFD on the lag, and it's a separate RFC, which is today not available with OpenVSwitch, but OpenVSwitch does support BFD today. It's been supported since version 2.4, but the lag BFD on lag is a future requirement. And if we want to go even like BFD support with OpenVSwitch today has been tested at 100 millisecond level, which is sub-second, which is not bad. But if you want to go to 50 millisecond or below, you're probably looking at offloading, and you want to maintain that latency and jitter. For BFD, you're going to have to look at BFD offload to the NIC at some point. Going a step further, looking with high availability deployment for the VPE. In this case, you're taking 2 nodes, 2 OpenStack compute nodes, and you want to ensure no, as Greg has pointed out, we want to ensure no single point of failure in this use case. And so you have 2 PEs, the VPE 1 and 2 on separate compute nodes, and you have your customer edge routers are now connected, dual homed to both the PEs. So if one PE goes down, they can sync up with the other PE. And you can see that to ensure this kind of behavior, you have a protocol, Virtual Router Redundancy Protocol, VRRP, enabled between the VPEs. And they're also running BFD between the 2 PEs to detect that a PE is going down and to recover from it really quickly. And BFD in this use case is being used all over the place. Not only between the PEs, also between the PE and the P router, and in addition, at the L2 layer, over the bond. Bonded links where we want VFD to be turned on at the LACP link level. And I'm going to hand it over to discuss scale. Back to Andrew.
So the second key thing that we would like to talk about is scale. So we want to be able to transition from our physical, which can offer thousands of services, onto the virtual to offer the same thousands of services. So clearly we need to meet the unit costs and reduce and meet our goal of reduced or higher efficiency. We're looking to have the same number of, in this case, VLANs. So what we're trying to describe here is layer 2 domains. So when we connect to external networks with a layer 3 provider edge router, we connect to lots of different layer 2 domains. The way that we identify services on these layer 2 domains is through VLANs. But we also have in our solution, and most cloud providers have this, is they have a layer 2 domain, their own layer 2 domain, to connect servers and to connect applications on those servers. So now we've got clashing requirements. So we want to connect and offer services to lots of other customer layer 2 domains over the top of our own layer 2 domain. As well as, and we want to be able to host lots of virtual PEs. So one virtual PE can connect to multiple layer 2 domains. In our case, we want lots of virtual PEs connecting to even more layer 2 domains, and we want to be able to switch interchangeably between them very, very easily. So if we look at so OpenVSwitch is not able to do that. Well, not with our implementation of code. And the network switching fabric, we had to employ some other kind of technologies, and in this case, we deployed an EVPN, an overlay technology on our networking fabric. And also, we negotiated with our attached customer domain to add another tag. So really the solution here is Q&Q. So we have an extra VLAN tag that identifies a customer layer 2 domain, and we can switch that over the top of our cloud-based domain direct to the virtual PE. So now we've got a much more scalable solution to connect our many virtual PEs to lots of other layer 2 domains. And the other key technology that we used here as well is, once again, SRIOV. So SRIOV allowed us to bypass, essentially, our OpenVSwitch. And we also had the added benefit of getting higher performance, so much higher packet per second performance by bypassing our OpenVSwitch limitations in the kernel. The trade-off, however, is that we've had to deploy a lot more ports. So unfortunately, when you're in these projects, you have to make some of these design trade-offs, and this is one of the trade-offs that we've had to make. But we are looking for alternative ways of more efficiently offering virtual PEs to ensure that we can still scale the same way that we have at the moment with the SRIOV technology. So now I'll pass it on to Anita to talk a little bit through about what these options are.
Thanks, Andrew. So now let's go back to the OpenVSwitch solution that Telstra could not deploy, and look at what things have been done already in OpenStack, as well as things that are coming pretty close. In this use case, you can see Telstra would like to scale to more than 4K VLANs, and they're using VLAN stacking on the customer edge. So we're talking about a large number of flows coming in, and which require Q&Q, or stacking of VLANs. This is a new feature been added to OpenVSwitch in OVS 2.7 and should be coming in OpenStack fairly soon. And in addition to that, what VLAN tagging is typically used by the OVS and by OpenStack to identify multi-tenancy. And so typically the bridges would strip out all existing VLANs coming in and inject a VLAN tag to identify the multi-tenant in this, or the tenant in this use case. But what Greg has pointed out from Juniper's point of view, his VPE essentially needs those Q&Q tags, those VLAN tags, to stay intact, because that's how the VPE identifies a customer, and that's how it identifies a service. And then it is able to put in the right MPLS label and ship it out on the core side. So we need to keep those labels those VLAN tags intact. In order to do that, there's a new feature called VLAN aware VMs, which was introduced in Newton. And that enables VLAN trunking on the OVS bridge, going out towards the VPE, on all the interfaces going out towards the VPE. So instead of stripping the VLANs, they leave them intact, and they add an additional VLAN tag to identify the multi-tenant, and enables trunking all the way up to the VPE. So now the VPE can get all its VLAN tags intact. And looking at the SRIOV solution that finally was deployed at Telstra, in that solution, there were some issues as well, from the sense that most NIC vendors today strip the VLANs for the VF. That's done by default. If you're using a virtual function, they're stripping the VLANs, and you cannot turn off VLAN stripping today unless you're using the PF, the physical function. But that becomes really expensive for SRIOV, because that implies that VPE is now using the entire NIC. You cannot share that VPE, you cannot share that NIC between two VPEs. And that's exactly what Andrew was pointing out, that they have to use a whole lot more NICs in order to support this. Instead, a new feature was added called VF Trusted, or promiscuous mode. And with this feature, which is coming in Pike, now you can turn off VLAN stripping at the NIC VF level. And this would allow you to now share the VFs between the PEs. And so the two features, just to reiterate, VLAN aware VMs for Newton and SRIOV trusted VFs coming in Pike are going to solve the VLAN stripping issues and allow you to send the whole VLAN stack directly to the VPE. And you can see over here that it's enabled for all three data paths. So if you're using OVS or OVS DPDK, your OVS bridges are now not stripping. They have VLAN aware VM enabled and can ship the entire tag, as well as if you're using SRIOV with VF Trusted, you can ship the whole stack in. And this is just an overview of the two technologies that we discussed here. And I will not go into too much detail, but it is more for review at a later point to look at all the new features added. And I will hand over to Andrew.
So to conclude, we've described what some of the business problem is we set out to do. And we showed how using out-of-the-box technology, we weren't able to achieve or meet the requirements that we were seeking. And some of the trade-offs that we've made, at least in the short term, to deliver upon our solution. And we are actually right now in the process of operationally accepting our solution in production, which is pretty exciting for our project. And we have also described some of the potential options that we'll be looking for in the next 6 months, or 6 to 12 months, to try and make our solution much more efficient into the future. And that concludes our presentation.
We have time for questions. And I hope people understand that we're asking for your help. If there's any developers out there, especially OVS developers or RHEL developers, to think about the telco use case, the telco application. Can we get it down to any failure, any link failure, any wire, or any virtual machine or software failure fails over in 50 milliseconds, and to be aware that layer 2 matters, that VLANs matter, especially for our VNFs. So, but we have time for questions or comments.
So why are you so hell-bent on using Q&Q still as your service definition?
So Q&Q, I guess, while it does have some limitations, it has broad use. So when we're talking about integrating to other customer networks, their routers are not always the most up-to-date routers that we have. And so Q&Q offers a flexible solution in that regard.
I'm interested what the alternative is. I can give you another use case for it.
Well, yeah, I mean, I get this. We should do it, right? I'm not arguing. Q&Q and Linux support has been all over the place for about 10 years. So this needs to be done. I get that. But, I mean, the Q&Q is it's a legacy of GPON access methodology, right? construct, and to try and push that back into OpenStack wider community as like the service ID definition is not going to fly. Like it really is specific to telcos. So, and I mean, we see this all the time with our clients, and our solution kind of uses VXLANs within BGP, right? So for what you do is we'd probably just suggest putting a hardware top of rack to do what you're doing, and that we have a service ID that's off the side in an administration system.
Okay.
We don't have to deal with the same problem of
So-
having to keep that information inside the packet. Right?
Yeah.
So that's kind of our way around.
Yeah, it's interesting. I mean, if I briefly, I mean,
Sure.
we can't take it out because what we're talking about here is a router, putting a router in the cloud. PE router, I happen to do broadband a little more than I do PE. And the router has to see the VLANs because they're in the physical network. We can encapsulate them, or we can like strip them and recreate them, but it's part of the information in the current network.
It actually, in our use case, it actually solves some other business problems as well. So probably not the full picture, but
no, it's hard.
It's a
I
good
hear
point.
you.
It's a
And
good point.
OpenStack is resistant.
And, and the performance is a lot better with VLAN Q&Q than with VXLAN. Just forwarding performance.
Interesting.
I know who your switch is using, but that's not true.
OVR. Yeah, another question?
Sorry, I work for the NBN, and we've got the same problem with Q&Q. We ran a lot of problems that you just discussed. How many VPs can you run on your host?
How many what?
How many VP? The question is, how many VPEs can we host on our compute? At the moment, with the scaling that we're after, so at the per VPE, we're looking at 2,000 VRRP sessions for connecting to customer networks, and we're hosting two per compute.
Yeah, so you mentioned, I don't know if people heard that the NBN is a new broadband backbone in Australia. And so for broadband, you don't need the VRFs and the MPLS that he's talking about. So maybe I'll do better. Come, we'll talk about it more if you like. Broadband's kind of another story, but more questions? Comments?
I got a simple question. It seems like you should virtualize the PE to achieve flexibility as well, but in the end, to meet the functionality, you have to use the SRIOV and sacrifice something.
Right.
Maintain the same functionality as a time-based solution today. So what is the business benefit really for the virtual PE?
Good question.
It is a good question. It's a transition phase that we're looking for. So part of also what we're doing with our project is educating a side of the business that doesn't typically use IT, not on a day-to-day basis. So while with these design trade-offs, you may not get all the direct benefits that we're hoping for, we're getting a lot of side benefits that make it quite worthwhile. So we're educating a lot of our staff in not only OpenStack, but in Linux and IT systems in general. And this provides a good vehicle. Also, it provides us a good vehicle to offer new types of services. So while with a virtual PE use case, we've had to make these different design trade-offs, I think it gives us a platform where we can put in service chaining as new features and new service offerings much more cheaply than we could today.
Yeah, I mean, it's the first application in the cloud, it's the hardest, the most expensive. Once the cloud is in place, now all of your packets are going through the cloud. All these other great applications that people build are available, east-west, low cost. So the first one is the toughest, but that's what Andrew's lucky enough to be, putting up the first network, cloud, integrated application. Good question. We have time for more?
Maybe 2-3 minutes.
Maybe one or two more other comments? Does anyone want to develop improve the development environment? I'd love to talk about that too. Yeah.
This might be just a little bit down a rabbit hole, but I think you mentioned that the Q&Q forwarding performance was quite a bit better than VXLAN forwarding performance. Can you quantify that, or can you put any meat around that?
Yeah, so we've seen about 2 to 3 times better performance, but this is just the kernel. You're looking at just the kernel, no hardware offload options, but just Q&Q with respect, comparing Q&Q with VXLAN performance. VXLAN is 2 or 3 times worse than we've seen with VLANs, Q&Q stacking.
I mean, I think it comes down to just another encapsulation. So
Just another encapsulation,
every
and
time
that's what
that
the
costs you a
VPE
little bit of compute.
Well, yeah, but I didn't know why one encapsulation is much cheaper.
Well, you want me to take that? So VXLAN is IP. It's a VLAN
UDP.
inside IP. So you have to, if the router has to, or the vSwitch has to process VXLAN, first it looks at the IP, says, you know, what IP is this coming from, what's inside this encapsulation. And then it sees the layer 2, and then it makes the layer 2 decision. So it's like 2 decisions. The Q&Q is no IP.
It's at the L2 layer, just add
So
another
if you
header.
can see it, then you don't have to peel the IP off. Is it a deal breaker? I don't know, but it will cost you a little. Yeah.
But VXLAN can scale a whole lot more than a single VLAN tag.
And we're not going to say your whole cloud has to run at layer 2.
Right, right.
You go.
It's a
So
layer 2.
we will get the VXLAN in there eventually.
So if you're going data center to data center, you want VXLAN. But if you're within the data center and you're just doing broadband connect, you can do L2.
Yeah.
I'm just curious why your future strategy was around things like peak placement and protocols and not looking at things like containerization, peers, and SDN, and maybe things like distributed vRouter and other technologies to actually extend the capability.
Yeah,
Another good question.
That's kind of a big one. What you're asking, like, what is our general strategy to be like regular SDN, vRouter? Right. Sure. So what we're doing here is we're trying to get the first one, the first cloud running, the first VNF, the first real mission-critical, super valuable virtual router in the cloud. And we had to compromise. But the point of this presentation is that we don't want to compromise in the future. We want to use all the SDN technologies. We want the overlay. We want a vRouter in the host operating system. We want to have our cake and eat it too. So, for sure, we're on board with it's got to be like a regular OpenStack application. But still has to fail over in 50 milliseconds. Still has to let us see, I'll say, more than 4,000, flows, layer 2 flows. No, we're on the path towards, it's a special application because it has these requirements, but it's just another, virtual machine or container in your cloud.
So we're looking at it. It's not part of our presentation today, but we are looking at it. And we have sister projects looking at SDN, pure SDN as well. So it's not in isolated, it's just for the presentation we've focused on one aspect of it.
Good. All right, great. Well, thank you very much for your time.
Thank you.